You can go there and just watch it. Okay, so we have covered good amount of ground on that linear algebra and NumPy. We'll have more linear algebra coming. But before we jump in and understand the data science, right, we need to understand a little bit of distributions, or more descriptive statistics and more inferential statistics we need to understand. So today I'll actually show you a little bit of what do you call it as distributions, and then I'll show one example, one complete end-to-end data science project example, so that you will get more clarity on what we are going to encounter in coming days. Okay, so why am I trying to I showed you some introduction end-to-end process, and again I covered some topic, and now I am again covering some theory, and again I am going to show you end-to-end, because there will be many dots in AI project. We need to connect all those dots first. If you connect all those dots, you know what you are doing, then it is easy to learn. Okay, so we'll see that today. So there are probability distributions. We cover binomial and normal distribution extensively, because we are going to use normal distribution very extensively in our AI queries. Rest all are also used, but those are very rare. Okay, so first we need to understand what is distribution. Suppose that we are it's a birthday and we are actually celebrating chocolates, biscuits, and ice creams in a classroom. So student 1, right, some person X went in, and to student 1 he gave 2 chocolates. For student 1 he gave 2 biscuits. Okay, and student 2, he gave 2 ice creams and 1 biscuit. And again student 2 want 2 chocolates also. So 5 items student 2 got. And student 3 got 3 chocolates, and student 3 got 1 chocolate. That means he distributed different items among different students. Right? Student 1, student 2, student 3, 3 different students, and he distributed different items. Right? So if we want to understand how many biscuits were distributed, how many chocolates were distributed, how many ice creams were distributed, that becomes the items distribution. Okay, now each student how many items got, that actually becomes the student's the distribution of food items got by students. Right? So in a data set there will be different distributions. Right? So in simple English, if we have to say, distribution means giving away things, or kind of holding some things, and we wanted to see them visually or statistically. That's called as distribution in statistics also. So if you look at this graph, student 1, right, got 4 chocolates. Student 2 got not chocolate items. They can be chocolates, they can be biscuits, they can be ice creams. Student 2, 5. Student 3, 4, like that. Okay, this is food items each student got, the distribution of food items each student got. Okay, and then the count of each food item distributed, like if I wanted to see, I distributed chocolates, biscuits, and ice creams. I wanted to see how many items I distributed. This graph is going to show that total count of each item distributed. Biscuits how many, chocolates how many, ice creams how many. If you look at this, we can look at the distribution numerically and visually both. See this part is all numerical. This part is all visual. Okay. So now when we can actually look at distributions numerically and visually, there are some kind of theoretical distributions. Okay. So far you are good, right? What is distribution you understood, right? Any questions there?
No, sir.
Yeah. Normal distribution is simple. The same whatever the English words meaning, the same thing. but visually we wanted to see or numerically we wanted to see is the thing. Why visually? Because we will have millions of numbers in the data. So what are we looking at? Only one column, right? This 4, 5, 4 I represented visually. This 3, 7, 3 I represented visually. These are the items. This is called as bar chart. On the x-axis we have taken the items and y-axis is the count and the bar height is the distribution, the amount of distribution to happen. Okay, so distribution is simple. English word is what distribution meaning is. The same thing in statistics also. Okay, so when we know distribution, right, there will be theoretical distributions. Theoretical distributions means in our basic classes we have looked at mean and standard deviation and try to understand data using mean and standard deviation, because in the data we try to find out a landmark and a scale. Right? Landmark is the mean and scale is the standard deviation. If you take one data point, how far it is from mean is the z-score, z-score, right? Z-score is nothing but, is it one standard deviation away or two standard deviations away or three standard deviations away? That's what we are trying to see. In the negative side or positive side. If it is one standard deviation less, right, we will actually represent this side. One standard deviation more will represent this side. Okay. So from the data itself, we try to pick up the landmark and the scale, right? Like that. When you look at a data's distribution, if it is in some shape or some form, you can actually make some inferences out of it. You can understand data, right? By looking at data distribution, you should be able to understand data. By looking at mean and standard deviation, we try to understand data. Similarly, by looking at distribution also, we should be able to understand data. So for that reason, there will be some theoretical probability distributions, we call them as. In one point, I'll actually highlight again. No, I'll say the probability and count are synonyms. Okay, I am trying to demystify or trying to simplify the concept and make it clear. I don't care what the definition is and all that. We are not going to deviate from definition, but I'm trying to make it simple. Okay, probability and count are simple at one level. At one level, right? When you start at the beginning, right? Probability and count are same. So we are looking at probability distributions here, binomial distribution and normal distribution. Whether you say probability distribution or count distribution, it is same. You remember this. It is similar, not same, it is similar. Count distribution or probability distribution is similar. Okay, why it is, I'll show you in a moment. Okay, so we are looking at probability issue. They are nothing big. They're nothing big. It is just that the count distributions only. What is this? Food items, biscuits, chocolates, ice creams, count distribution. Right? Each student, how many items got? That count distribution. This and its probability distribution are same, are similar. Okay? They named it very fancy. Probability distribution, binomial normal. Okay? So we'll see that. Why this many names and this many distributions is, if data is following binomial distribution, you will have a formula to understand data, or you will have a formula to calculate the probability. Or if the data is following normal distribution, you will have some inferences from the data. It is like this. If you look at any politician, generally we look at politicians and try to compare them with maybe some people, these BJP guys will compare politicians with Rama, and modern age whatever politicians or social activists, they try to compare them with maybe Lal Bahadur Shastri or maybe the Gandhi, like that, right? So why are we comparing one person with another? Do you know why are we comparing in the political world? Why are we comparing? Can you tell me? Somebody?
Yeah, when we compare, we'll take someone as a reference so that when we compare, we may get some better idea about the other person relative to that. That's where we compare.
Yes, yes, right. We get better idea. One thing, when you are explaining to somebody else, right, it becomes easy, right? The understanding becomes easy for the other person. The understanding becomes easy. Same concept here also. Human beings generally compare and try to see. They need a scale, right? We always need a scale. On a scale, what every item we wanted to see on a scale. That's where we compare people, right? And even the people around us also, when we look at somebody or talk to somebody, oh, this guy is like that person, right? So maybe this guy is also going to behave like that person, right? So we'll form an opinion, and based on that we'll actually act. So that actually generally happens, with me generally it happens, right? So in statistics also, in numbers also, when you are analyzing data also, you need some ideal personalities or ideal distributions. When I say ideal distribution, right, you know something about some distribution, you try to see your data and how close this data's distribution is to the theoretical distribution, and then use those formulas, try to use those formulas to assess this data's behavior or this data's properties. Okay, our goal is to understand data, right? We took data, we collected data, then we are trying to understand data. Once after understanding it, we'll do pre-processing, then we apply machine learning algorithm and bring out the predictions, classifications, whatever. So we are trying to understand how to understand data. To understand data, we need some scale or some ideal distributions with which we'll compare. These are the ideal distributions: binomial, multinomial, uniform, Poisson. Poisson it is. They call it as Poisson. I don't know why. English is a little weird language. And then normal. And there are many 18 distributions are there. But if you know normal distribution, right, that's good enough, I would say. Okay. Rest all are not a big deal. We can learn. If you understand binomial and normal, that is good. So I'm going to cover binomial and normal. So when an experiment, we need to understand what is random variable before we understand probability. This term is too heavy, but there is nothing big. If you understand this count on y-axis and items on x-axis, that is the same thing. Whether it is probability distribution or count distribution, it is same. Don't get confused. Okay, the probability distribution is a big word, but the meaning is very small. Okay, so let us try to understand what is random variable also. Random variable also simple thing only. When I look at most of the science and mathematics, most of it, 90% of it, it is all jargons. The names are very fancy. When you look at the concept, it is very simple. Beyond 90%, that 10%, right, that is really good work. Okay, so the random variable is nothing but when you try to do an experiment, right? When you try to do an experiment means I throw a coin. I wanted to see what I'll get. When I throw a coin, will I get head or tail? I wanted to predict. Okay, so if I throw a coin 5 times, okay, if I throw a coin 5 times, what happens? You throw a coin 5 times, so you'll have all heads coming, all tails coming, right? First tail coming head, rest of the 4 tails, or maybe second head, second. Give me 1 second. So, when we throw a coin once, right, we'll get either head or tail. Okay. If you are trying to calculate probability of getting head or tail, right, that getting head or tail is the random variable. Getting head or tail, that is a word, right? That's not a value. Generally, when you do programming, right, a variable will have a number assigned to it, or a string assigned to it, or a Boolean value assigned to it. But in statistics, when you do experiment, the outcome we are trying to assess, we actually say it as a word. Getting head is one value for the random variable. Getting tail is another value for the random. X is equal to getting head. X is equal to getting tail. X is a random variable that actually is trying to hold a string that is, that describes the experiment. Getting it? Getting it, right? Any questions there? Is my statement clear? Is my statement clear? Can I move on?
Yes, sir.
Yes.
So when you throw coin 5 times, right, what happens? You may get 0 heads, 1 head, 2 heads, 5 heads. 1 head and rest are tails, 2 heads and rest tails, 3 heads and rest tails. Right? These are all values the X can hold. Right? That's just a string like this. Getting 0 heads, getting 1 head, getting 2 heads. So to see number of heads when we toss coin 5 times, the discrete random variable, we call it as discrete because when you throw coin 5 times, right, you can count total number of outcomes. Right? Total number of outcomes will be maybe 32, around 32, I think. 32 only, maybe, not maybe, 32. Because first coin when you throw, you may get head or tail. Second coin also 2, third coin also, like 5 times, or 5 coins or 5 times. So when you throw each time, 2 possibilities. So 5 into 2 into 2 into 2 into 2, right? If you throw 2 times, right, what happens? Head, head, tail, tail, head, tail, tail, head. 4 we got, right? 2 into 2. If you throw thrice, right, you will get 2 into 2 into 2, right? Like that. 5 times 2 to the power 5 is the number of total possibilities. So you will get 0 head, 1 head, 5 heads, 2 heads, 3 heads, like that. When I say 2 head, right, 3 tails, like that. So again, like first coin, third coin, first coin, second coin, you can count the total number of possibilities. So that is called as discrete random variable X. What is X here? Getting 0 heads, getting 1 head. It's a string. Okay, it's a sentence. Okay, that is called as random variable. Huh? You got clarity, right? Random variable. And then there is a continuous random variable. This discrete random variable, the experiment's outcomes are limited. We can count. Then we call it as discrete random variable. The experiment's outcomes are not countable, right? If you take stock price, right, of HDFC, you are trying to the probability, the problem we are trying to solve is what is going to be today's HDFC Bank's stock price, right? So stock price being 1295.02, stock price being 1295.03. If you take these two numbers, right, in between also there will be million numbers, billion numbers. We can infinite number of numbers. If you take real numbers, because when you look at stock price, it's a real number, right? So the experiment is about a real number, then you call it as the variable which is trying to assess it or hold it is called as continuous random variable. Got it? Did you get the difference between discrete random variable and continuous random variable? Did you get the difference? Any questions here?
No.
So if you want to assess temperature in a year or temperature on a day, is that a continuous random variable or the variable which is going to hold the string or the sentence, is that a continuous one or a discrete one? Continuous, right? So temperature can be between 20 and 42 in India, right? 42 or 43, right? But if you want to assess uh, marks of a student. Marks of a student. Is that a continuous or discrete? Discrete it is, right? So from 1 to 100 or maybe 1 to 25, right? So like that it is. Okay. So simple. Random variable is nothing. You know, these x is the random variable, and x is going to hold, you know, getting 0 heads, getting 1 head in a continuous situation, right? X is going to hold a range, stock price between, you know, 1295 and 1296, because exactly measuring a stock price may be a bit difficult, or calculating probability of a continuous random variable at exact point is not possible. I'll show you why. Okay, when you look at the graph and all that, right, we'll see. But we can calculate, but it is not going to be that accurate. If it is a range, right, definitely you will be able to calculate. You know, and there will be confidence interval also. This is called as confidence interval, and there will be confidence percentage also. Okay, we'll talk about all that in future. So this is called continuous random variable. Now probability distributions. Now we know what is random variable, and we know what is distribution. Now we are looking at binomial distribution. So when your experiment, your conducted experiment is discrete in nature, right? So discrete in nature means the outcomes are countable. Then we can assess that. We can assess the probability of happening something using binomial distribution. The binomial distribution gives you discrete probability distribution. What is probability distribution again? Let me show you the example first, and then we'll go into the theory. So I threw a coin 5 times. Right? There will be 2 possibilities here: head or tail, head or tail, head or tail, and head or tail, and head or tail. Total 32 possibilities are there. If I have to assess what is the probability of getting 0 heads out of 32 combinations, these are 32 combinations, right? What are those combinations? First head, rest all are heads. First head, rest all are tails. This one head, this one tail, this one head, this one tail, this one head. Like that, there will be 32 combinations. Out of those 32 combinations, we'll get only one combination which will be all heads. Right? So 0 heads, right? Or all heads or 0 heads. So 0 heads means all tails, right? 0 heads, only one possibility. Out of 32, it is one possibility. 1 by 32 is the possibility. So we are actually taking favorable events divided by total number of events. That's the probability. Okay. I'll make one statement here. I'll reiterate the same thing again. When you are calculating probability, right? When you are calculating probability of 0 heads, are getting 1 head, are getting 2 heads, are getting 3 heads, the denominator is going to be 32 only. Do you agree with that statement? Did you understood that statement? When you are calculating probability, numerator may change, but denominator will stay the same for all probabilities, for all different values of the random variable x. Do you agree with the statement?
Yes.
Right. So in a minute, right, I'll say whether you take probability or count, in favorable count, it is same, I'll say in a moment. Okay. So be prepared for that. And that's, I'm actually trying to simplify the probability concept. When you go beyond a certain limit, right, probability is a little complex, but for machine learning, data science, if you understand this concept well, that's good enough. 90% of the times we'll use, maybe 99% of the times, this probability only. Okay, we'll use joint probability, conditional probability, but it is in NLP and very rare. It is already implemented. No need to understand it. If you understand this concept, right, that is enough. Okay, so I threw 5 times and I calculated probability of getting 0 heads. It is 1 by 32. The same thing can be calculated using the probability density function. The probability density function and probability mass function, 2 terms are there. Okay, probability, when you are calculating probability of a experiment using the experiment's outcomes are discrete. The density function is called as mass function also, probability mass function also. Terminology, it is nothing big. Probability density function means what? A formula that calculates this probability. The probability density function is a formula that calculates this probability. What I did here to calculate the probability, I looked at the combinations, right? 0 heads combination out of 32, only one. I calculated 1 by 32. If I want to see one head combination, right? First one can head, first throw maybe head, second throw maybe head, third throw maybe head, fourth throw, fifth. So I'm actually trying to chart down all those combinations and then calculating the favorable events, and anyway denominator is going to be same, right? 5 by 32. Instead of doing this charting down thing, if you can use some formula and calculate the probability, this formula is called as probability density function. So this is only 5 times. I can actually chart down, right? Like this, getting 1 head, getting 2 heads, getting 3 heads. Like that I can actually chart down and calculate favorable events. If I am doing for 100 times, I'm throwing coin 100 times. What happens then? Can we be able to calculate this? If I throw coin 100 times, can we be able to calculate these combinations? Is it possible? Yes, no? No, right? So we need some formula. What this guy, whoever actually found out the binomial distribution, Bernoulli, his name is I think, no, not binomial distribution, he actually did multiple experiments and came up with a formula that can actually calculate this total probability, right? So this formula, right? Ncr, p to the power of r and p to the power of n and q to the power of n minus n. The small n is the success rate, number of successes. N is the total number of trials or experiments, right? So the probability of getting head is 1 by 2 because there are 2 possibilities. Out of those 2, only one is in favor, right? Getting head. Probability is very, very simple concept, I would say. Right? We'll generally see how many. If you have like a bag of balls with blue color and green color, 4 balls blue, 4 balls green. You take out one ball, what is the probability if you ask? We'll say equal, right? 4 by 8 and 4 by 8. There are 4 there, 4 of this color, 4 of that color. If you have 2 red balls and 4 green balls, if you take out, right, you will say more probability for green balls because there are more green balls, right? So it's a simple concept, it's a ratio. Probability is nothing but a ratio. Okay, so when you throw a coin, what is the probability of getting head is 1 by 2. Tail is also 1 by 2. So the P is the probability in favorable probability for that event, for that whatever experiment we are trying to conduct. And then this N is the capital N is the trials, number of trials, 5 times, right? Small n is the successes, 0 heads. So NC0 is going to be factorial n by factorial n into factorial capital N minus n. Or generally we should be saying that R. I actually copy pasted this formula from somewhere else and it was like this. So let me try to show you the NCR formula. You all know it, but you would have forgotten. I'm just trying to remind. So this is like, right, this formula is like N, I think I should, NCR P to the power of R, Q to the power of N minus R. Right? Here N is 5 times we conducted experiment and we are trying to see 0 heads. Okay, so 5C0, 1 by 2, right? Getting a head is 1 by 2 to the power of 0, and getting a tail is 1 by not getting head. Q is not getting head. P is getting head. Q is not getting head. Right? 1 by 1 minus P to the power of 5 minus 0. Right? So this NCR is factorial N by factorial R into factorial N minus R into anything to the power of 0 is 1. This is 1 minus 1 by 2 is 1 by 2 to the power of 5. Right? This is factorial 5 by factorial 5. Generally, what is factorial 5? 5 into 4 into 3 into 2 into 1, right? And factorial 0 is 1, right? So this is factorial 5, factorial 5. It is 1 by 32. We got the same probability here using this formula, right? So this formula, this is the binomial distribution formula. When data is binomially distributed, you can use this formula. What is binomially distributed? I'll show you in a moment. Okay. So instead of calculating manually, we are using some formula to calculate probability. That formula is called as a probability density function. That formula is called as probability density function. Density. What is density? See this graph. This is the height is the density. The formula is calculating this height. I'll show you in a moment. The probability, the formula is calculating this height. The density of the bar it is calculating. That's where we call it as probability density function. Okay. So we have seen the formula here. Right? Now let us look at the graph a little bit. Okay. So probability of getting 0 heads is 1 by 32. We already know. Probability of getting 1 head is 5 by 32. Probability of getting 2 heads is 10 by 32. How do I know? I used this formula and calculated the rest of the probabilities. If I try to do a bar chart, right, between the random variable and the probabilities, what is random variable? X is equal to 0 heads, X is equal to 1 heads, X is equal to 2 heads, X is equal to 3 heads, X is equal to 4 heads, X is equal to 5 heads. Okay, that is random variable. You know, writing it on the graph is difficult. So I said X is equal to 0, X is equal to 1, X is equal to 2. Okay, the bar height is the probability. See this 1 by 32, 5 by 32 and 10 by 32. 0 heads is 1 by 32, right? Like that it is. I'll actually say one thing, right? If I take out the divided by 32, will the graph shape change? Will the graph shape change if I take out the divide by 32?
No.
Look doesn't change.
Look doesn't change, right? Anybody else has got concerns for it? What I'm saying is, let me try to take a screenshot and explain. This is key. This is very important. This is very important in simplifying the concept. There is nothing big in these distributions and probabilities and all that. What I'm saying is, this is the graph, right? So I'm actually saying that I'll take out this denominator. Okay, I'll take out the denominator and try to do the graph again. Will the shape change? Will those heights will change? Or the look, the way it is looking right now, will it change?
No, sir, no.
No. Anybody disagrees with the statement? Anybody disagrees with the statement? Good, right? So now you can see, right? What is 1, what is 5, what is 10? Out of 32 combinations, one combination is 0 heads combination, all tails. Out of 32 combinations, 5 combinations have 1 head, either first trail or second trail or third trail or fourth trail or fifth trail. Out of 10 combinations, out of 32 combinations, getting 2 heads has got 10 combinations. So it is the count, in favor count is the y-axis. Whether you take probability or count, the shape will not change. Do you agree with the statement now? Whether it is probability or count on y-axis, the shape of the graph will not change. Scale may change, but shape will not change. Got it? Got it? Yeah. Can we say that probabilities and counts are kind of similar, kind of synonyms? Can we use them as synonyms? In that context, whatever I explained.
Yeah.
Right? Vaguely we can actually, right? So is there anything in probability distribution that very fancy word? It took a lot of time for me to understand, but no, there is nothing there. There is nothing there, there is nothing in probability distribution. They are actually trying to see the counts of each of the, each of the occurrences there are the trials outcomes, right? there will be experiments, and for each experiment there will be different kinds of bar heights. And if the bar heights are actually forming a bell curve, right, you call that as binomial distribution. If the bar is the if the experiment's outcome, if it is forming this kind of a bell curve, right? Why am I saying is a bell? It is like bell, right? Like that, right? It is like temple bell. And when you look at these, because of these probabilities are the counts, we have got this shape. Getting 2 heads, there's a lot of probability. Getting 3 heads is also a lot of probability. But getting 4 heads, less probability. Getting 5 heads, less probability. So when data is distributed like a bell, and the variable, the random variable is discrete, you use binomial distribution formula to calculate probabilities, and the distribution is called as binomial distribution. If the data is forming this kind of a bell curve, right, you call the distribution as a binomial distribution. What is distribution again? How many each item? How many each item? How many? What is the item here? Getting 0 heads, getting 1 head, getting 2 heads. Right? 1, 2, 3, 4, 5 heads. Got it?
Only after coming up with the chart, I will be knowing whether it is a bell shaped or other shaped. So how
Yes.
can I proceed with when I solve the problem? How can I know I can go for a Bernoulli or this binomial distribution, sir?
We will actually look at the distribution. We will actually look at the graph and then decide. So we have visualization tools, right, ma'am? We actually did it. Already we did bar graphs, right? When you do bar graph, right, you will understand whether it is a binomial distribution or not. When you say it is a binomial distribution, if the x-axis is holding the categories, right? See this? These are categories, are countable number of values are there on x-axis. Then you say it is binomial distribution. On x-axis, if the values are continuous, right, then you say it is normal distribution. We'll talk about normal in a moment, but
okay,
we do a graph and then understand. Then we come to a conclusion.
Okay, sir.
Yeah. So even in real time, right, when I took the politician's example, we see the person's behavior over a period of time, and then we'll try to assess or actually try to describe. This guy is like Gandhi, this guy is like Modi, and this guy is somebody else, right? So we look at data, we look at the bar graphs or histograms, and then decide which distribution it is and which formula to use to calculate the probability. Once we know the distribution, right, we can use that formula to calculate the probability. Whatever data we have, we'll try to plot with that data, and then we find a bell curve. Then you can immediately take this formula and calculate the probability of that particular whatever number of experiments or outcomes we are trying to look at. Okay, so this is binomial distribution. Let us look at the definition a little bit now. Okay. The binomial distribution gives the discrete probability distribution P of P n given n, right? N is, I think R I should have taken, R given n, of obtaining exactly n successes, small n successes out of capital N Bernoulli trials, we call it as. When an experiment's outcomes are countable, you call that as Bernoulli trial. Okay, so or only 2. Bernoulli trial is only 2, where the results of each Bernoulli trial is true with probability P and false with probability 1 minus P. Only 2 outcomes are there, then we call it as Bernoulli trial. If more than 2 outcomes are there, we can use the same formula, but it is called as multinomial distribution. Binomial distribution we have seen. When you throw a coin, there will be two outcomes only. Right? You call that as binomial distribution. What the heck today? Hello? Too many calls in the early morning today. I don't know. Okay, so when the experiment's outcomes are only 2, true or false kind of a thing, then we call that as Bernoulli trial or Bernoulli experiment. When the experiment's outcomes are more, and we use binomial distribution formula, and we call it as binomial distribution, and we use binomial distribution formula. But when experiments outcomes are more, when you throw a die, right, there will be 6 outcomes. And when you throw a die, 6 outcomes. The outcomes are discrete, right? If you are trying to do probability, or you are trying to calculate probability of getting only one, when you throw a die, 2 or 3 or 4 or 5 or 6, you can use the same formula, but it is called as multinomial distribution. Okay, multinomial distribution and binomial distribution are same. You know, the formulas are same, but the experiments outcomes are, you know, 2 or more. If it is 2, we call it as binomial. If it is more, we call it as multinomial. Okay, so the probability density function. What is probability? A function of a distribution that shows the density of the values of our data is called as probability. So the function of a distribution that shows the density, that shows the density, this height, the bar height, right? When you put the values into the formula, right, what is it giving? This height it is giving, this height it is giving, this height it is giving, this height is. So that is the density. That bar height is the density. So that is called as probability density function. Okay, and it is called as probability mass function also. When it is, you know, discrete random variable, you call it as mass function, and when it is continuous random variable, you call it as density. I forgot the name. Probability mass function and yeah, probability density function and probability mass function. Okay, so in a continuous variable, we call it as probability density function, and a discrete variable, you call it as probability mass function. They are all not, you know, different. The names are different, and if you try to Google it and see, but definitions are very confusing. When you look at statistics definitions, right, they are very confusing. But when you clearly see and not spend some time, right, there is nothing big. Okay, so any questions here so far? On binomial distribution, any questions? Okay, good. So normal distribution, when the variable is continuous, right? The random variable is continuous. When I say random variable is continuous, we are trying to predict a stock price or temperature on a certain day, or, you know, rainfall on a certain day. These are all experiments with random variable, continuous random variable. Continuous random variable means the values are continuous. You cannot, you know, you cannot say like, you know, 20, 30, not integer, they're real numbers. Okay. So when the experiment is conducted, I have good example also. Okay. When experiment is conducted, right, there will be many values coming in, right? So if you take this example, when you throw a coin, maybe throw a coin 5 times, maybe 0 heads is coming, 1 head is coming, 2 heads is coming. But you did that experiment many times. You throw 5 times a coin, collected the data. Again throw 5 times, collected data. Again throw 5 times, collected data. This is experiment. Okay. So you did maybe 100 times, right? 100 times. Then, you know, you will see that, you know, out of 100 times, 10 times this will happen, 5 times this will, 1 time this will happen, like that. Okay. So when you did the experiment, you will get bars like this, but you can connect all those bars and do a line like that. Okay? Then your graph may look like this. Okay. Same graph, you can do it as a line graph also. When you do a line graph, right, it looks like this. And in general, when the variable, the discrete random variable is continuous, sorry, the random variable is continuous, you generally get this kind of a line, because when you conduct the experiment, right, if you see a rainfall experiment, let me try to take a screenshot and explain. if you see a rainfall experiment, right, there may not be negatives there, right? So right, 5 centimeters rain, 1 centimeter rain, 2 centimeters rain, 4 centimeters rain, right, 3 centimeters rain, and 4 centimeters rain. If you collect data over maybe 10 years, right, over 10 years, how many days the 1 centimeter rain fell? Maybe, you know, a small bar. How many times 2 centimeters rainfall fell? You know, a little big bar. How many times rain fell? Right? How many times 4 centimeters rain fell? How many times 5 centimeters? Okay, so this is 1 centimeter, right? There will be 1.1 centimeters, 1.2 centimeters, 1.3, 1.4. There will be many numbers between this, you know, 1 and 2. So there will be bars like that. A line, a line, a line, a line, a line, a line, like that. Do you agree? Do you agree the graph will come like that? What is the height here? You know how 1 centimeter, how many times, right? So how many times on y-axis? I'm getting confused. Count, day count. Day count on y-axis. Okay, how many days the rainfall fell, right? So there will be lines rather than bars, right? If you take real continuous numbers here and try to plot it over 10 years, right? Or 10 years, there will be lines, not bars, right? When you draw this, right, you can actually join all those tips of those lines, and then, you know, you can draw that like that, right? So in a normal distribution, right, when you say it is a normal distribution, when the random variable is continuous, you say the distribution is normal. You call that as normal distribution. And generally normal distributions are represented like this line graph, because each of the bar is going to be like line, because there are many continuous values. Got it? Got it? Any questions there? Any questions? No? Can I move on?
Yes, sir.
Yeah.
So a normal distribution, or you call it as Gaussian distribution also. There will be, you know, algorithms name, you know, by we'll cover one, you know, Gaussian based anomaly detection. It is nothing. We'll actually assume that data is following normal distribution or Gaussian distribution and use the probability density function, this function, right? What is probability density function again? It calculates the density of the bar, you know, height of the bar, or width or height, both we can say as density. Okay, but when you are now, if it is a if you take this bar as rainfall bar, right? Sorry, this graph as a rainfall graph. If I try to predict, right, what is this f of x? It is a prediction. If I want to predict what is the rainfall at a, sorry, what is the probability of getting 2.1 centimeters of rainfall today, right? I need to know mean and standard deviation. So from historical data, I'll calculate mean, right? Mean may be 3 centimeters or maybe 3.1 centimeters. Standard deviation may be 1, right? And then you substitute these values, right? 1 by 1 into 2 pi, I don't know what is the value of pi, e power minus 1 by 2, right? 2.1 minus 3.1 divided by 1 square. So this is how you calculate the probability. But when you calculate probability at one point, right, that's going to be a kind of line, like that, line, a line, not a bar. So generally for the continuous random variables, right, we calculate between range. What is the probability of getting a rain between 2 and 2.1 centimeters? How can you calculate that? you do an integration. What is integration? Derivative is a kind of slope calculation, right? Velocity and slope, those things can be calculated using derivatives. Integration, right? Integration is a very different concept. Let me try to explain what is integration. There is a curve like this, okay? And you wanted to calculate the area under this curve. We know how to calculate area of a rectangle, right? What is the area of rectangle? What is the formula of area of rectangle? Formula to calculate area of rectangle, area of square.
All side square.
Side square.
X square, right? If it is x, the length of it is x, right? Length and width. If it is a rectangle, length and height, length and width. L into W, right? So we know how to calculate area here, but for a curve we don't know how to calculate area, right? Then what we will do is we'll try to find out a formula for one rectangle which is very thin in nature. Right? The width is very thin. The width of that rectangle is very thin. It is line only, right? So we'll try to find out a formula for a rectangle which is very thin that can actually do these bars here. Okay? We'll find out a formula to do a bars in this, curve, which is nothing but this formula. Okay? The probability density function is what? At given x, what is the probability it is calculating? What is the probability means the height of the bar, right? So that is the formula, right? We'll integrate it over from here till here. If it is 0, if it is 3, to find out the area under this curve, what are we doing? We are calculating area of this line, area of this line, area of this line, area of this line, area of this, all these lines and summing up, right? First line's area is A1, second line's area is A2, third line's area is A3. Like that, there will be infinitely many number of, right? Maybe 1 billion numbers, 1 billion, maybe infinitely many number of A's. I shouldn't be putting infinite here. Now maybe 1 million or 1 billion. So by calculating each line's area and summing all of it, right? Summing all of it, we'll get the area under this curve. You got it, right? You got this point, right? Any questions there? Any questions there? No, right? So now, if you want to calculate area under this curve, right? We know that to do this line, the formula is this one. So we can actually use integration. Integral of 0 to 3, right? This formula 1 by PDF function sigma square root of 2 pi e power minus 1 by 2 x minus mu divided by sigma square. If you do this, right, you will get area under this curve. In a normal distribution, area under the curve is 1. Okay, that is given. Okay. When data is normally distributed, it will form a bell curve. That is the rule. And then to calculate the probability of a normally distributed of a random variable in a normally distributed data, the formula is this. And to find out the area under the curve, we can actually do integral from 0 to 3 using the formula. Do we need to calculate it? Do we need to know integration? No, no need. I'm just trying to explain the concept here, because in some interviews and tests, they'll have questions like this. Okay, no need to know integration right now. Okay, don't be worried. And if I have to calculate the probability of getting a rain between 2 and 2.1 centimeters, take the same thing, right? Integral of 2 to 2.1, the same formula, 1 by sigma square root of 2 pi e power minus 1 by 2 x minus mu whole divided by sigma whole square. Okay, so what are we doing there? Right, if that is the bell curve of the rain, right? It is from 0 to 3. I want to know the probability of falling rain. How much probability is there to between 2 and 2.1, right? I'm actually trying to calculate the area under that curve. That area I am trying to calculate. To calculate that, I'll use probability density function and integrate between this range. Okay. So what is integration? It is just that the summation. Is everybody there?
Yeah,
Yes.
yes.
Yeah, I lost. Yeah, I lost power. I lost power and came back. No, I rejoined. So I was explaining, right? This integration and all that, right? So what are we trying to calculate here? The area under this curve. The area under this curve we are trying to calculate. The integration is nothing but summing up of a formula's outcome or a minute values outcome over a period of whatever, right? So draw clarity, right? Any questions here? The integration part, right? You don't need to no need to remember. The formula also no need to remember. If you remember, right, that's going to be better. Okay. Formula also no need to remember. So the normal distribution, right? When you say the data is normally distributed, when the data is forming a bell curve and the data is a continuous random variable, the random variable is continuous, then you say it is normal distribution. The normal distributions can be of any shape, right? I have drawn 3 bells here. The first bell has got a mean of -2, right? Mean will be somewhere here. Okay. You can hear me clearly, right? It is on a mobile net.
Yeah, we can.
Yeah. So the mean is going to be in the middle. Okay. -2. Okay. And for this blue line, right, the mean is 0. Okay. For the red line is also mean is 0. But when you see the 3 graphs, right, one is like that, right? One is actually very spread a lot. Another is spread, the spread is close. And the third one is in the middle. And if you look at the standard deviations or variances, on the blue line, the variance is less. So it is actually steep. The like the curve is actually steep and it is close to mean. Okay. And the second graph, the mean is 1. So the standard deviation, the variance is 1. Right. So it is the red line one. It is actually spread is a little more. If you see the yellow one, right, the variance is 5. See that the variance is 5. The spread, see this line, the mean is somewhere here and the values are actually spread a lot, right? So on the last graph, the green graph, the mean is -2 and variance is 0.5. So when mean is negative number or positive number, it is actually moving aside, right? Moving aside. It is these 3 graphs are aligned in the center, but this graph is like to a side, right? Generally, when we analyze one column, we'll get only one graph. But I'm just trying to show you different graphs there with different means and standard deviations. The standard deviation or variance is going to decide how steep the graph is or how much data is close to mean. If you see this data, right, most of the data is close to mean. Got it or confused? Got it?
Sir, should we infer that the blue line where the variance is almost or very less, is that the highest probability if we pick any random? Is that what we need to infer from this one?
Yeah, what do we need to infer from this? I'll explain that in a moment. In a single statement, right? the predictability of the data in the blue graph will be more accurate. Predictive power is going to be more, and the predictions are going to be more accurate because variance is less. See, this is like human beings only. Some people are very stringent and very strict and disciplined. You can predict the behavior of that person in different situations, right? Right? Is that true statement? People who are very disciplined and strict in nature, we can predict their behavior in different situations, right? Do you agree with the statement?
Yes, sir. Yes, sir.
Yes, sir.
Right?
Yes, sir.
If a person is a fickle-minded, you cannot predict that person's behavior. So this yellow line is a fickle-minded person's behavior. Blue line is a strict, stringent person's behavior. So the patterns are very close to mean. Always the patterns are very close to mean. The data distributions are very close to mean. Okay, so you can predict what is going to be. Your predictions are going to be very accurate also in this particular situation, right? So what we can infer, I'll show in a moment. In a single statement, I said that. Let me take the example and talk about it and then stop. Anyway, I started. So there is a 3 sigma rule, right? When data is normally distributed, it forms a bell curve, I said, right? And when it forms a bell curve, right, 68% of the data is going to be close to mean within 1 standard deviation. If you subtract 1 standard deviation and add 1 standard deviation to mean, suppose that mean is 7, standard deviation is 1.2, right? If you subtract 1.2 from 7, it is 5.8. 1.2 to the 7, it is 8.2. 68% of your data points, suppose that they are scores in a quiz, right? 20 students appeared in the quiz, right? 68% of 20 students is how much? 7, 14, maybe around 13 people. 13 people's scores, 13 students' scores are going to be between 5.8 and 8.2. Did you get the statement? Should I repeat? Should I repeat?
Yes, Rama, please repeat.
Okay, let me take a screenshot and write it down. Suppose that the mean is 7. We have seen that quizzes, right? The mean is 7 and standard deviation is 1.2. Suppose that the data is normally distributed. When I say data is normally distributed, there are scores between suppose that 3 to 10. There are scores between 3 to 10. There's one person, right? I will take 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there is one person who got 3 score, 2 people who got 4 score, 5, 6, 7, 8, 9, and 10. Okay. If data is like this, suppose the data is like this, that means data is normally distributed, right? If data is like this, right, I can surely say that within 1 standard deviation, there is going to be 68% of the data. What is data here? Students, right? Students and marks. Maybe student marks, student score, right? Student score is the data. 68% of the data is going to be within 1 standard deviation. That means what? What is within 1 standard deviation? Mu minus sigma and mu plus sigma. We are trying to understand data by looking at a graph and a mean and a standard deviation. That point you need to remember. Mean, standard deviation, and a bar graph. We are trying to understand data. So 7 minus 1.2 and 7 plus 1.2 is what? 5.8 and 8.2. 8.2. Right? 5.8 and 8.2 are these numbers, 5.8 and 8.2. So I can say on this data, 13 students are going to be within this range. 68% of the data is going to be within 1 standard deviation when data is normally distributed. Okay, when data is normally distributed, approximately normally distributed also, right? 95% of the data is going to be within two standard deviations. What is two standard deviations? 7 minus 2 into 1.2, right? And 7 plus 2 into 1.2. 7 minus 2 into 1.2 is 2.4, right? So 2.6 and 11.4. And 95% of the students' scores are going to be within. So almost like, around 18 people, or maybe 17 students' scores are going to be within this range. So we are trying to understand how the data is, how the data is distributed. When data is normally distributed, understanding data is going to be very easy. Did you guys get this concept a little bit? So there is a 3 sigma rule. When data is normally distributed, within one standard deviation, 68% of the data is going to fall. Within two standard deviations, 95% data is going to fall. Within these 3 standard deviations, 99.7% data is going to fall. Did you get this point? Yes, no?
Yes, sir.
When data is normally distributed, that is actually the key point. You need to remember, when data is normally distributed, only this rule applies. 3 sigma rule applies. Okay. So let me take another example, one simple example, right? And then I'll stop and ask for questions and all that. And on Monday also, I'll recap this for 1 hour, sorry, half an hour, and then practically we'll see with code how to actually do this graph and how to look at whatever, right? Monday or Tuesday we'll decide. I have to talk to Keshwa and Balabhaskar and decide. If anybody is celebrating Diwali on Sunday out of our team?
No, sir.
Saturday, right? Everybody is celebrating it on Saturday.
Yeah.
So we'll actually try to have a little maybe practice session for 1 hour and then recap of this thing maybe half an hour. Light session. If somebody wants to go home and come back and all that, right? It is going to be, they're not going to miss anything. And from Tuesday, right, we'll come back to full speed. That's how we plan. Okay. So excuse us, right? Tomorrow, day after tomorrow, no practice session. I'll put that into the group also. And you practice and come back with questions on Monday. I'll also be there on the practice session on Monday. Okay. That works, right? That works, right? Ma'am, you are the one who's going to join regularly, Mahesh and you. So that works, right?
Yes, sir.
Yeah. So here, right, I took some data of employees, right? This employee ID and designation, right? Director, junior developer, senior developer, and then experience and salary. I took salaries in such a way that it is actually normally distributed. When I tried to do a plot between 20,000 and 30,000, see this, the salaries are real numbers. Actually, I took the integers, but in reality, they are real numbers. There will be point something also, right? So when you really calculate everything properly, there will be real numbers. So on x-axis, I have taken ranges rather than categorical values, right? If you look at this graph, x is equal to 0, x is equal to 1, x is equal to 2, those are values, right? But here, these are ranges, right? From 10,000 to 20,000, how many? There are no people who are getting 10,000 to 20,000 salary. From 20,000 to 30,000, how many? From 30,000 to 40,000, how many? Right? I actually counted, or we actually grouped the, or I filtered data and then tried to count the values, and there is code there. I will see that. And how many we actually did this graph. If you look at this, it is actually forming bell curve, right? Do you agree that is a bell curve?
Yes.
Right. So I can say the data is normally distributed. What data is normally distributed here? I am saying data is normally distributed, right? What data normally distributed?
number.
Salaries,
Salary.
right? Salaries, right? So on x-axis, whatever we took, that is the data, right? That is the data we are trying to analyze. Salaries. Y-axis count it is, right? Count. Okay, number of employees is count. So salaries is the thing we are trying to understand. Salaries data is normally distributed. What is the advantage of salaries normally distributing? Salaries being normally distributed. If you want to give a hike, right, you will know how many people are within some range. We'll see that in a moment. Okay. So now I'll calculate mean and standard deviation of this data. What is data again? Salaries of the students, salaries of the employees. Now I calculated mean, which is 54,735.78, and I calculated standard deviation. What is standard deviation? On an average, if you pick a data point, how far it is from mean, how far it is from mean, how far it is from mean. That is the point you need to remember. Standard deviation I calculate. What is it saying? If you randomly pick a data point, what is data point here? Somebody's salary. That guy is going to be this far from this much. You add and subtract, right? You add and subtract. The person's salary is going to be going to fall between maybe 30,000 to 70,000 on an average. Okay, it is at a high level. Okay, so now I applied 3 sigma rule here because the data is normally distributed, right? So I applied 3 sigma rule. What is 3 sigma rule? Within one standard deviation, 68% of the data is going to be there, right? Within one standard deviation, what is one standard? Mu minus sigma. What is mu? 54,735. Sigma is this number. When I subtract this from this, right, I got this one, 37,000 whatever. Okay. When I add this to this one, I got this number. That means 37,596 is a salary. 71,875 is another salary. The 68% of the total number of employees are going to fall in this bucket. Did you get that point? 68% of these employees. How many employees are there? 30 employees. 68% of 30 is how much? I think I calculated it. I think I have it in the sheet. 68% of 30%, 30 employees is how much? 3 into 7, 20, yeah, around 20, right? 3 sevens are 21, right? Around 20, 19 or 20. 19 employees, salaries are going to be within this range. What is the advantage of knowing that? If we are trying to give hike, right, we know that this range, how many people are there? How much percentage if we give, how much effect is it's going to put on our budget, we'll understand. If you have 1 lakh employees in your company, this bell curve is going to be very useful. I think in your companies, big companies, right, they do bell curves and they talk about bell curves. I don't know how many people understand what is bell curve and what is the use of it. I don't know, but if your data, if your employee salaries are forming normal distribution, the management will know, for how, if I give, this range people, right, 37,000 to 71,000 range people, if I give 5% hike, how much impact is going to be there on budget? 90, there will be a bucket here, right? Low salaried budget bucket. If I give high salary, hike, more hike also, it may not affect because I know how many number of people are falling here. So in between this, right, 68% of the people, right, 19 people are falling here. Rest of the 11 people are going to fall in this range and this range, right? So maybe 5 people or 6 people are low salary, 5-6 people are high salary. If I give 10%, 20% hike also for these 6 people, it's going to be okay. For these people, if I give 2% salary hike, this is going to be okay. By looking at the data, by looking at the bell curve, we are actually assessing how much salary should be given a hike, to people. And here, within one standard deviation, 68% of the data, 19 people. Within 2 standard deviations, 20,000 to 89,000, 95% of the data. Like maybe, out of 30, maybe 28 to 27 people will fall in this range. Only 3 people, 2 to 3 people will fall in the outside thing. Within 3 standard deviations, 99.7%. Okay, so bell curve, even though it is forming bell curve, it is not exactly normal distribution, but still we can use the 3 sigma rule to assess what is happening there. That is statistics. You always not take every rule as taken for granted. You try to use it, even if it is here and there a little bit. Got it? Got the use of the data distributions, and you understood what is binomial distribution, what is normal distribution, and all that. Any questions? I am done for the day. I am actually going to stop recording and take questions.